we're going to see if we can get through today. Might be able to get a good chunk of this done so tomorrow you can have some math Excel work time. Maybe don't have to do anything over the weekend. All right, so the biggest difference between this lesson and what we were doing in section 6.1 is in 6.1 we used z-scores and critical values of z because we knew the population standard deviation. So if you look back at the original title of that 6.1 lesson, it says that population standard deviation was known. If we do not know the population standard deviation, we cannot use the z-score chart and those critical values. So we're going to talk today about what happens if we don't know that population standard deviation and all we have is a sample standard deviation. Okay, so if that is the case, we're going to use what we call a t-distribution. The t-distribution formula to find a t-score instead of a z-score is essentially the same formula we've been using. If you look at the two formulas compared, the only difference is on the top we're subtracting our means, our sample mean minus our population mean. That's the same in both. In the denominator, it's here standard deviation of the population divided by the square root of n. For our t-score, it's a lowercase s, which is the sample standard deviation divided by the square root of n. So that's the only difference between the two formulas. If you want to find a t-score versus a z-score, it's just not the population standard deviation, it's a sample now. So there's that formula, and t sub c, if you see that, just means a critical value of t that we'll be finding in our chart in a little bit. A lot of this information for your t-distribution is the same as what we saw with our standard normal curves. The mean, median, mode are all going to be in the same place, and you're going to see that bell curve shape. So it's bell shaped and it's symmetric to the mean. The total area is still equal to 1 underneath the curve. The biggest difference, and we'll see this on the next page, is if you compare an actual normal curve, a z curve, to a t curve, is the ends, the tails, are going to be fatter. They're not going to be as much of an asymptote as close to the axes. They're going to be a little higher above the axes because when we're talking about a t-distribution, we're talking about samples, not population, which means we need to leave a little extra room for error in those tails with the information that we have. Okay, so you can see that on the next page, the difference between the two. Degrees of freedom is something that we're going to talk about a lot. It's the number of free choices left after a sample statistic is calculated. We don't do a lot with degrees of freedom other than knowing what it is to be able to find our t-distribution value that we're looking for. To calculate degrees of freedom, it's just your n, your sample size, minus 1. So again, it gives us a little extra room for error because we're dealing with the sample. At the bottom here, the blue curve is our standard normal curve. And then you can see we've got a couple other curves based on a certain number of degrees of freedom. The more degrees of freedom you have, the closer you are to a standard normal curve. The less degrees of freedom you have, you can see it gets a little flatter in the middle and then a little more area in the tails, again, just to adjust for the sample that we're looking at. Okay, so that's the difference between a z and a t if we look at those distributions. Okay. All right, so on your t-distribution chart, you guys have that in your packet of definitions and whatnot. Let's say we want to find a critical value for 95% confidence level. Yes. 6.2. Are you? Oh. So we're going to be trying to find those confidence intervals again that we were finding in the last section. In order to do that, you need to find the critical value. So if you guys can find your t-chart. The first one here is we're going to find a 95% confidence level. Our sample size is 15. So first thing that you have to do, once you know your sample size, your n, you're going to take that and subtract 1 to get your degrees of freedom. So if n is 15, degrees of freedom is n minus 1, 15 minus 1, and that gives me 14. Okay. That's what you're going to find on the side of the chart, your degrees of freedom. And then on the top of the chart, you're going to look for the level of confidence that we're going to be using to create our confidence interval. So you're going to find 0.95 for 95% on the top. You're going to go down until you get to degrees of freedom 14, and then it's circled on there. You guys should see 2.145 on your chart. You see that okay? So find the critical value for a 90% confidence level with a sample size of 22. So if my sample size is 22, what's my degrees of freedom? 21. So those are the two things that you're going to be looking for on your chart. On the top, you're looking at 90%, so 0.9. On the side, we're looking at 21. And I get 1.721 is my critical value of T. Now you'll see as you go down to degrees of freedom at the bottom, they start to kind of jump around. Once we get past 40, we go to 45, 50. So let's say you had like a degrees of freedom of 43, something like that. This previous slide kind of tells you what to do if that's the case. If the degrees of freedom is not in the table, use the closest value below that number on the table. So if you had degrees of freedom of 43, the one below that would be degrees of freedom of 40 is what you would use. So the number less than that, not equal to it. Okay? Make sense? Great. All right. Margin of error formula. This should look familiar. This is the same as our margin of error formula for our critical values of Z. The only difference, instead of a Z now, we have a T that we're finding on our T distribution. And instead of a population standard deviation, we have a sample standard deviation. Okay. And again, the margin of error is what we're going to add and subtract onto the sample mean to get that confidence interval that we're looking for. All right, so calculating the margin of error, let's practice. So we're using the following formula: critical value of T, sample standard deviation, divided by the square root of n. So you need to use your chart to find that critical value of T using the given information. I have a confidence level of 95%. My n is 16, so what's my degrees of freedom here? 15. Okay, so then those two pieces of information I can find on my chart to get my critical value of T. So you're going to find degrees of freedom 15, go over to 95%, and that is 2.131. Okay, and then we plug it in. 2.131 times S over the square root of n, square root of 16. Type it in your calculator. Thank you. Calculator here. We're doing 6.2 right now. And you should get margin of error of 2.66. Actually, I can get the whole number here, 375, if I don't have to round it at all. All right, you guys try the next one real quick. Okay, you should get margin of error of 4.537. 2.896 is my critical value for T. There. Degrees of freedom 8. Confidence level 98%. Any questions? Okay. All right, so now we're going to take this and kind of put it all together. So remember, if we have a margin of error, we add and subtract that to the sample mean to get this confidence interval. The confidence interval is always estimating the population mean. If you are finding a confidence interval, that's our goal, trying to figure out what is that population mean. So this is out of your textbook. These are essentially the steps that we're going to be using to find that confidence interval. If you don't have the sample mean or the sample standard deviation, you would have to calculate that first. Sample mean isn't too bad to get. Sample standard deviation, you guys remember back in chapter 2 with that huge table of values where we had to do like multiple columns. So a lot of times if you had to calculate it, you would just use a calculator to do that. But you'll be given it in most cases. Then we find the degrees of freedom, which gives us our critical value of T. We find the margin of error, add and subtract it to the sample mean, and that estimates my population mean. Gives me a range of numbers. Remember, the bigger your confidence level, the wider the interval. So you can be more confident that that interval contains the population mean, but wider interval isn't as great of an estimate. Okay, so first problems we're going to do, we did ones like this in the last section. It says use the confidence interval that's already created here to work backwards to find the sample mean and the margin of error. And we're just going to do one of them because it is the exact same as what we did in the last section. So remember, when we have this interval, in this case it's 14.7 to 22.1, the sample mean, our x bar, is going to be right in the middle of the two. So you're just doing a midpoint or an average of the two values that you have. So if I want to find x bar, add them up. Divide by 2. Find that middle value. I get 18.4. Then, if you want to find that margin of error, that's what was added and subtracted on. So that's twice. You can see that in this picture here. It's the difference between your sample mean and then either extreme on your confidence interval. So you can use either pair there, just find the difference to get that margin of error. I'll just do the 22.1 minus the 18.4. And you get 3.7 is the margin of error there. Units, whatever that represents. Okay. Make sense on that? Okay, so we won't do the second one because it's the same calculation there. All right, so let's actually put it all together now and find that confidence interval. So in this problem, it says you randomly select 16 coffee shops and measure the temperature of coffee sold at each. The sample mean temperature is 162 degrees Fahrenheit with a sample standard deviation of 10 degrees Fahrenheit. Construct a 95% confidence interval for the population mean temperature of coffee sold. Assume all temperatures are normally distributed, and then we'll interpret our results again with that little statement that we practiced before. All right, so number one, I need to check my two conditions that we've talked a lot about. So either my sample size is bigger than 30 or it's normally distributed. Is one of those two true in this case? Yes, it's normally distributed, so we're good, okay? The next thing that I'm going to look at is my standard deviation, because what kind of standard deviation I'm given is determine what kind of critical value I'm going to use, a z critical value or a t critical value. Here I am given the sample standard deviation. If you are given a sample standard deviation, I immediately know I'm using my t values, my t distribution, my critical values from there, okay? All right, so things that I know that I'm given. 16 coffee shops, so that's my n. And if you know n, you very quickly can get your degrees of freedom. What's your degrees of freedom then? Just one less than that, 15. I'm given a sample mean, that's an x bar of 162. I am given a sample standard deviation of 10. A confidence interval of 0.95 is my 95% confidence interval. And then I can use that to find my critical value of t from my distribution chart, okay? So find 95%, find 15 degrees of freedom. So 95 is that middle column at the top, 15 degrees of freedom on the side. You see your critical value is 2.131. Okay. Once you've got all those values, we can calculate our margin of error, which is going to tell us what to add and subtract to that sample mean to get our interval. Formula again for that was the critical value of t times the sample standard deviation over the square root of n. So 2.131 times s is 10 over the square root of 16. Type it in our calculator. And my margin of error is 5.3275. I'm going to round things the same way everything in this problem is rounded. So it's 5.3. And I know there was a question yesterday about what this represents. So in this problem, everything is a temperature in degrees Fahrenheit. So our margin of error is 5.3 degrees Fahrenheit here. That's going to be our estimate or our temperature range that we're ultimately getting for the answer here. Okay. So X bar plus and minus that margin of error, which in this case is 162 plus and minus 5.3, and that's going to give me my confidence interval. 162 minus 5.3 gives me 156.7. We'll label it degrees Fahrenheit. And then if I add it, 167.3 degrees Fahrenheit. Okay. And remember, this is an estimation for the population mean. Our mu is what we're estimating here. Okay. So the interpretation of that is that we can be 95% confident, or you could say there is a 95% probability that the mean, actually I'm going to say the population mean for all coffee temps is between these two numbers that we've just found, 156.7 degrees Fahrenheit and 167.3 degrees Fahrenheit at coffee shops, et cetera, if you want to expand on that a little bit more. Okay. Questions there? All right. So what we're going to do, I think we're going to stop there for today because we've got our wonderful shortened periods. The next problem on here, we're going to make a warm-up for tomorrow. So you can start it now if you want to, or just you can load it back up when you come into class tomorrow. That's fine. You're going to be doing 3 different confidence intervals for this problem from the given information. A lot of it's going to be the same, but you're going to compare a 90, a 98, and a 99% confidence interval and explain the differences that you see in the widths. Okay, so that's a warm-up tomorrow. We'll have a couple more problems. It won't be a super long lesson tomorrow, and then you guys should get, I'm guessing, between 20 and 30 minutes of Math Excel work time tomorrow. Hopefully get a good chunk of your homework done, okay? So 6-1 is due tonight. 6-2 is due Monday night. And then you have a quiz just over confidence intervals on Monday. It is open note. You can work together on it. There is an individual portion as well, but you can discuss the individual portion. That's all I can say right now, okay? But open note, Monday, chapter 6. Okay. All right, and I'll do cell phone lotto. Yes.